we're looking at the half-bridge inverter, but actually applying real components to it and looking at its more realistic operation. So here's the standard ideal half-bridge inverter, and we have these ideal voltage sources and these ideal switches. Those aren't real in real life. We can't use those. So first let's look at this part and see how we can change this into real components. We want two voltage sources and we want them to be half the value of VDC, and then we want this ground connected here. How can we implement this in real life? We can, instead of using the voltage sources, actually use a capacitor here and a capacitor here. Then we have to connect the V source, VDC, over here. So this is your actual VDC. Assume that these voltage capacitors are the same value, then this will charge them up equally. And then as long as we connect this point to ground, we'll have half the voltage here and then half the voltage here. So using this setup, capacitors and then your voltage source over the whole voltage here, we can achieve effectively the same thing. And assuming that everything's balanced, these voltages will be approximately the same. What about the switches? We don't have ideal switches in real life. We need to use a real switch. We're going to use MOSFETs here. So let's redraw these as MOSFETs. And we're going to assume N channel. So, and we're going to call it Q now, so Q2. And remember that there's a body diode, which is anti-parallel, an anti-parallel diode that goes in this direction. And usually the current through the switch will go this way, but it actually depends, can go either way. Let's draw it here as well. So here's our MOSFET. And here's our gate controlling that. And draw our body diode, called Q1. Also note that we changed the load to simply an inductor, so we're going to work with that example. From this table that we had before, we're going to look at the same states. These are the same. So if just Q2 is on, we're going to get negative VDC over our load. If just Q1 is on, we're going to get positive VDC over our load. That's just like the ideal case. But when we're switching between these two states, in the ideal case, we instantly change between the two. This instantly turned off, this instantly turned on. But in real life, they're actually going to transition slowly. So this will be turning on or off, and this one will be doing the opposite. So for a very small instant, they will both be on at the same time and be able to conduct current. We know that that is this condition, and in real life, that is shoot through and that is bad. We do not want that. It's just going to put current through here and nothing goes to the load and it's a waste on our source. We want to avoid that. So what we do is actually add dead time. So I'm going to try to draw that up here. So first, we're going to turn on, let's say S1 is on for a period of time, and then S2 is going to be off. This is 0 and 1, 0 and 1. And during this period, when S1 is high, we're going to get positive VDC over 2 on our load during this period. Then we will want to switch between the two. But what we'll actually do is add some dead time, call this dead time, where S1 is off, and actually S2 is off as well. Before that was a violation of KCL, but because we have these anti-parallel diodes, these body diodes, we can still make it work. Current will still be able to flow. Let's say that current is flowing this way, so into our inductor. Then if current is flowing in this way, then it can actually flow through this body diode of our bottom switch. So we can get some current flow in this direction. For that instance of time, this will still be flowing even though both switches are off. So during the dead time, there are passive diodes that the current can flow through. If it's going the opposite direction, let's say it's actually flowing in this direction, well, that's okay too, because if it's flowing in this direction, it can go into this diode, through this body diode, and flow in this direction. If it's flowing through the body diode, it's still going to have some voltage over the system. But as you can see, which voltage it is depends on the direction of the actual load current. So during this dead time, if the current is going in the green direction, so the green direction here, the body diode is on, so there's a little bit of a voltage drop there, but not too much. But the voltage seen over the load is going to be this VDC over 2, just minus this little voltage drop. So negative VDC over 2, and then minus a little bit of a voltage drop, so maybe about here. So during that dead time, that's what we'll see during this period. Then once they've both fully turned off, we can turn back on the other one. We can turn on S2. S1 will remain off during this period. And that means that now we'll have the full negative VDC over our system. So now we'll go to the negative VDC and maintain operation during that period. Then if we want to switch back, we have to do the same thing again. We actually have to add in that dead time. So this will go back down. This will remain off for a short period of time. And let's assume that it's still flowing in the same direction. Then it's again going to go to that same voltage. We go to this value until we switch to the new value, starting the whole cycle over again. This would stay low, and then this would go up to the VDC once again. So from this dead time period, we can see that both switches can be off at the same time because we have the body diode for the current to flow through, but the voltage depends on the current. So it depends on I out. So if we use real switches, for example MOSFETs, to operate this half bridge, we want to operate complementary switching. But in order for that to happen in real life with real switches, we had to add in some dead time here. So this period here, dead time, where both switches are off, which allows them to fully turn off before we turn the next one on. And during that time, it will passively go through the body diode of the MOSFET, and whichever one it chooses depends on the load current.